Well, hey folks, how you doing? Welcome back to another episode of In the Loupe TV. I'm your host, Don Grandt, CTC Cutting Tool Counselor, here with another, hopefully, exciting episode. If you haven't yet, and you haven't subscribed to our channel, please do that. Formality, I always say it. Just hit the subscribe button, hit the like button, share it with anybody that you think will gain from this knowledge we bring as a cutting tool company. Hopefully you're enjoying these, and I hope you enjoy this episode. We're talking about drills. There's been a lot of comments saying, hey, I want to learn a little bit more about drills. So I'm going to do an episode, roughly about 15 minutes, on drills, point geometry, what makes a drill critical, and how to get a hole that is adequate for your application. Now, I do say adequate for your application because all holes are different. Not all holes are created equally, folks. They're different. So if they're different, we might be able to use different drills for different hole quality situations. That's what this episode's on. Can't wait. So please stick around, come back, and join us for this episode on all things drills. So, welcome back, by the way. So, if we're talking drills, the first question I get is it a drill or is it a drill bit? Well, let me just explain the difference between a drill bit and a drill, okay? First of all, a drill bit goes inside of a drill. So if you're doing general purpose things around your house, it's called a drill bit. You go to the hardware store, it's called a drill bit. It goes in a drill. If it doesn't go in a drill and it goes in a CNC machine or a Bridgeport or something like that, it is a drill. Everything we manufacture is a drill. Most people out there in the industrial world, it's called a drill, not a drill bit. You can call it a drill bit if you want, but we're just going to refer to it as a drill for this episode. Now we have to run to the shop and talk about drills in greater detail. So folks, we're at the shop, and what do we do at the shop? We talk applications. But before we talk applications, real quick, folks, stop making fun of my hat. This hat is like an old pair of shoes. It's always been with me. It's always going to be with me. It's actually even got glue holding it together. Love my hat. I'm not getting rid of my hat, and you're going to continue to see this hat throughout all my episodes. Just want to get that out of the way. Now we can dive in to applications on drills. So we need to understand something when it comes to drills, okay? A lot of end mills we talk about cut on the side, right? A drill cuts on the bottom. Only forces used on a drill, and I want you to think about this throughout this episode because there's a lot to cover with drills. The only forces that are muy important to a drill is the axial force. There's no side force. It's all axial force. So mainly with a CNC machine, it's in the Z motion. We're pushing down. So that is very important to understanding how a drill works and the best way to use a drill, because the point geometry and the end of that drill is going to create the most amount of pressure and force pushing up on that. So it's critical to get the right point geometry. This is where we're going to go into some high performance stuff later for the right drill. So drills come in all shapes, sizes, helix angles, point geometries. Some are split point, some are not split point. Some are high-speed steel, some are powdered metal, and then you get into carbide, and you can even get into PCD tipped and stuff depending on what material you're actually cutting. And so that is very important to start this episode off on drills with the material that you're drilling. Because we just talked about the point geometry briefly, and the point geometry is critical for that axial force, but it's also critical because all the different types of materials that we're drilling into make a different chip. Or what I mean is they have different characteristics for the chip, which means some are stringy, some are gummy, some are hard, some break, some don't break. So we have to accommodate that because a drill really serves three purposes. It makes a chip, it holds a chip, and it gets rid of a chip. So I think the best thing to start out with I said start out like twice. We're starting. This is going to be a long episode, and I hope we can close it out on drills, but we might have to come back to it a little bit because there's a lot with the geometry, and there's a lot that's going to help you make great quality holes. So the best way to start out is, what is the quality of the hole? What's the quality of my hole? I can't pick a drill. I can't choose a geometry. I can't look at all those things that a drill has to offer if I don't know what the quality of the hole is I'm drilling. Let's explain. First of all, if we just want to open up a pocket, drill a start hole, we really don't care what kind of drill we use. We just want to make sure it's big enough to put a hole in there. We can use high-speed steel. High-speed steel, cobalt, that's where we kind of go back to a little bit more general purpose. It's going to give us a good quality hole in certain materials, but guess what? It's flexible. Flexible can be good with a drill. It can be good with an end mill. Why is flexible good? Well, if your situation isn't very rigid, your setup's not very tight, and you think there's going to be a little bit of movement, then you might want to go with high-speed steel or cobalt. Why? Because it's going to take the movement. It's going to actually move a lot more. If you go with carbide or something else like that, carbide doesn't like to move. So let's just talk about high-speed steel and cobalt and where you might use one of those drills over a high-performance carbide drill and where their strengths are. So a hole quality has many different aspects to it to be high quality, medium quality, or low quality. Let's just start with low quality. Let's say the roundness of the hole is not very critical. Let's just say the straightness of the hole is not very critical. The finish of the hole is not very critical. Now there's certain levels of critical, so don't take what I'm saying verbatim like, oh, are you talking about a junk hole, Don? No, I'm not talking about a junk hole. I'm talking about a hole where maybe the quality or the critical features aren't as important. High-speed steel and cobalt, if you put a lot of pressure to it, because it's the point, it might want to walk a little bit. It might not be as round as you think it might want to be, depending on what kind of high-speed steel or cobalt. So therefore, you can get away with using high-speed steel or cobalt in a hole where the quality might be a little bit less. That still means that we got to pick the right geometry on a high-speed steel and a cobalt drill. The biggest part of that geometry being the point angle, the length of the point angle, whether it's split point, whether it's not split point, whether it's web thinned, what kind of reliefs, what kind of angles, and what kind of diameter on that tool. So let's just talk about a drill point really quick before we dive into high performance carbide drills and getting the best quality hole that you can. So a drill point really is creating all your force. What that point looks like on a drill is really going to determine how much pressure is pushing up on your whole system, right? Because it's all axial force. So the point is really generating 70% of the thrust force that's going through there. So what do we need to do? We need to accommodate the thrust force by doing certain things to the point and the point angle based on the material in order to get that to drill efficiently and as free as possible to get down to the bottom of the hole or to make a high quality hole. So let's look at a couple point angles, okay? The main thing I want you to understand about a point angle is the steeper the point, steeper, when I say steeper, it looks like more of a pinch to it. The steeper the point, the softer the material. The flatter the point, the harder material that you're going to drill. So if you're looking at a 118 degree point angle, that's 118 degrees, 118 degree point angle, it's more for general purpose, more for softer materials, 1018s and stuff like that. As your point angle gets flatter, then it's going to be for harder materials or more difficult to cut. Why is that? Well, the steeper the point angle, the longer the chip off the face of the cutting edge. The flatter the point angle, the smaller the chip, less force. Remember what I said? What we're trying to do is generate the least amount of force. So the flatter the point angle, the less force. Now, that I said that doesn't mean you want a 180 flat bottom. That's not going to work because they're going to bring in other issues. But what I'm saying is you don't want a 118, you don't want a 60, you don't want a 90-degree point for, say, some Inconels, Hastelloys, or some very hard materials. You want like a 140-degree point, 135 or better for harder materials. Just remember, the flatter the point angle, the shorter the chip on the cutting edge, and the better it is for harder materials. So now let's talk about going the other way with point angles. I said point angle going down to 140 degrees. Yes, that's for harder materials. Now if we go steeper, this is where your softer materials go. And why is this? Well, I'll tell you what, a 60-degree point is really good for cutting like acrylics and plastics and things like that. Why is that? Well, because you're spreading that load all over that point angle and you don't get the chipping, you don't get the fracturing, you don't get those types of issues. So a steeper point angle is for softer materials, a flatter point angle is for harder materials. Now, there's something called a web on the end of the drill. The web is what is creating all of the thrust force. That web in the center, how large that is what's causing the most amount of force on your drill. So what do we do as professionals and cutting tool manufacturers in order to reduce some of that thrust force? Well, we have to split. We have to thin that web in the center. We thin the web in the center, and the more you thin it, the less thrust force you have at the end. Not only are we thinning the web at the end of the drill, but we're also generating more rake on the end of the tool, so it cuts freer toward the center. All little tips and tricks to make a drill cut a little bit better when we actually do the point geometry on there. Point geometry is very critical to getting the right tool for the right material. That's why material-specific drills are the way to go when we step into high-performance holes. So what's a high-performance hole? What makes a hole high performance, or what makes a hole a quality hole? Well, straightness. It's critical, right? How straight is that hole, especially how deep is that hole, how straight it is. You got to maintain that straightness for as deep as that hole. If you go short holes, not as critical, but as you start going longer, it's very critical to get the straightness of the hole. This is where high-speed steel sometimes, you know, it's like a old dog in your house. You got to take it for a walk every once in a while. The drill likes to go for a walk every once in a while. Sometimes that's not as critical and you need to go with carbide. So the straightness of the hole is very critical. The roundness of the hole. How round is that hole based on the drill? Believe it or not, you can get very oblong holes with drills if you don't use the right geometry. So how round is that hole? Also, what does the finish look like on that hole? Finish is very critical. This is where we're getting into high performance. We need to have a nice finish on the hole. And last but not least, because there's a lot of things with hole quality, last is what is the diameter tolerance on that hole, and how well can we hold all those dimensions, straightness, roundness, finish, with that diameter, that hole size for a long time. So in order to do this, in order to hold all these quality features on a hole, what do we need to do? We need to put a lot of, I don't want to say bells and whistles, but we need to put a lot of features on material-specific carbide drills to make sure that we get a round, straight, burr-free, hole tolerance hole on a drill. There's also ways to use the drill to make sure that those quality features actually come out. So first, let's just talk about moving or making that switch from high-speed steel into carbide. Carbide's stable. Carbide's not going to walk. Carbide's going to create pretty much the hole, if you use the right speeds and feeds, that it was designed to do. The downside of a carbide drill is it doesn't like to move. It's not going to take any kind of movement with the fixturing. It doesn't like any movement in the holder. It likes good TIR because it's going to make the hole that it was intended to do. Now, what are some of the key features that create the right specs on that drill to create that hole? Well, first and foremost, it's the point geometry. Point geometry is designed for material specific, like we said before. So we're looking at the point geometry for certain materials to actually start it, create the less thrust force. We're going to run through this, the geometries on there. So the point geometry is going to create the less thrust force. The less thrust force on the carbide drill, the less walking, the less movement, you're not going to break it. Then we talk about the reliefs and the angles on the tool in order to generate the right chip thickness to break accordingly. So let's talk about a carbide drill, and first of all, let's just talk about, do we peck or do we not peck? Or like I say, to peck or not to peck? That is the question. Man, I've heard that so many times when it comes to drills. I'm sorry. I apologize that I just did that. That was not called for. I won't ever make a joke like that again. But it's a great question. Should you peck? Should you not peck? Well, let's just start out right away by saying a deep hole is usually anything that's over 4 times the diameter on the drill. So deep hole is where you're going to start looking at pecking. That's number one. Number two, you're also going to look at pecking based on the material. Now, why would I say the material? Well, all materials make a chip, right? Remember what I said a drill does? It makes a chip, holds a chip, evacuates the chip. So all materials make different shaped chips. Again, this is very important why we go with material specific, because what we want to do when you're doing a deep hole or you're drilling anything more than 4 times D is you want to make sure you break the chip into small segments, because if you don't break the chip, then you can't do number 2, which is to hold the chip, which means the flute can't hold the chip. So we need to break the chip. So how do we break the chip? Well, number 1, it's on point geometry. That's what we're going to try and do to break the chip. But here's some tips and tricks to also help break a chip when we get into 4 times D. Number 1, blast cooling through. Cooling through drills, high performance drills, cooling through, blast it through the chip or through the tip. Hopefully get 1,000 PSI, and it's going to help you break a chip. That's number 1. Number 2, if you're not breaking a chip, okay, you might want to feed it faster. Anytime you feed a drill a little bit faster, you get the curl on the chip, the material you're making from the cutting edge will curl quicker and it'll break. So don't baby your drills. That's one thing I want to tell you. Don't baby them. Make sure you feed them good enough to break a chip. Now, if that's failing, and let's say the cooling through is not doing the job, the feeding's not doing the job, what we might have to do is something called a peck cycle. So Don, let's just say, you know what we're not getting a straight hole, and we're not having those features. Well, first of all, a lot of people also ask, should I spot? Should I pilot? Should I do all these features? Now let's just explain what spotting is and what piloting is. So spotting is very different from piloting. Let's talk about spotting. When a drill starts, believe it or not, we design drills to self-center themselves. The point geometry on there is to self-center. How much? Usually up to 12 times D, you can run a drill without a spotting tool and it'll self-center itself. That being said, it might not give you the whole quality you're actually looking for. It might just walk a little bit at entry. So I'm telling you, can you use a drill up to 12 times D without spotting? Yes, you can. The geometry is designed to self-center it and spot. If the whole quality is not that good, or you did tend to walk at the beginning, you might want to spot. Now that's using a spotting drill that looks like this. That means you're putting a little start hole. You're trying to give that drill just a little bit of start hole. Now the critical with using a spotting drill is you always want to use a spotting drill that's flatter than the drill point geometry that you're using. Which means if you're running a 140-degree point, you want that spotting drill to be flatter, which means maybe 141 degrees or a little bit on the high side of it. So the outside edges of a carbide drill do not break, do not fracture, and do not wear down. You want the point to do the work first. The point is where it's going to guide it in. So when you're using a spotting drill, make sure it's flatter than the point that you're using, because you want to drive off that point and you want to give it a good start in the hole, and that's going to help you get a better quality hole. Now let's say you're using an 8x-D drill, it's coolant through and everything else, and you're drilling in a hole and you're still not getting the start, or you're getting a little bit off on the hole. Well, what you might want to do is use a pilot drill. Now what's a pilot drill? So a pilot drill does one better. Basically, you drill 1.5x-D or 3 times with a shorter drill. Get that hole to start, a little bit larger than the diameter you're using, and then your drill actually falls into that hole and it already has a good guide. Okay? Now, this is where some of the fun stuff starts. Now, everybody has a tendency to make drills with different margins on them. Margin is the cylindrical round on the outside of the tool. That's a margin. It doesn't cut. It's cylindrically ground. It has zero relief in that margin. What it does is it stabilizes the drill in the hole. Okay, when it's cutting, it stabilizes the drill in the hole. Now, some people put 1 margin, some people put 2, some people put 3. Our drills for steels have 2 margins. Why is this beneficial? Why does this make a great hole quality? Because if you put a pilot a little bit larger and you drop a double margin drill down into that pilot, guess what? It acts like a bushing. It really starts your hole off nice and straight, and that pilot will act like a bushing and guide that thing all the way through. So look at double margin drills sometimes. And if you have a double margin drill, you might want to hit a pilot. So again, a way to make a good straight hole 2 ways. Number 1, like we said, a point is designed to self-center itself. Okay, it is. It can self-center itself. If you want a better quality hole, get a spotting drill. Spotting drill is going to be flatter than the angle you're doing, drives the point, gets it going in. If you really want to go up and you got that pristine quality hole, put a pilot in there. Pilot's going to guide your drill straight through the hole, and you're going to get great primo quality of that drill. Wow, I really know that was a mouthful. There's a lot on drills. The quality of the drill, the quality of the material, the coating that goes on the drill is also critical. Now let's just throw in some bonus stuff. There's a lot on drill. Should you ever drill a hole without coolant? No, no. Always put coolant in your hole. A drill, believe it or not, is the fastest metal removal tool that we have. It's going to remove material faster than anything else we can do. That generates a lot of heat, right? That's why coolant through on carbide drills is great. Blast that coolant all the way down to the point. That point's going to get very hot, and also that point is the workhorse of the drill. Understand that. So never run drills without coolant through. Another big critical feature with a drill is TIR, run out. Make sure you have the right holder. The right holder with the drill is going to give you some critical advantages to actually drill in a straight hole and a quality hole. We also talked about single margin, double margin, and triple margin. I'm going to tell you also, with a double margin drill, you're going to get a rounder hole. Now, why do you get a rounder hole with a double margin drill? Believe it or not, both margins, as I said, are cylindrically, that's kind of hard to say, cylindrically ground, which means they have no relief on them. They're there for support. So when you're drilling a hole with a double margin drill, believe it or not, the front rake is creating the geometry on the hole, and that back margin is actually kind of burnishing that hole and making it a lot rounder. So double margin drills, when they're designed, make a rounder hole and actually give you a better finish. And here we go. Here we go. Ready for this one? A double margin drill will hold a tighter tolerance in your hole. How tight? Reamer tolerance? No, but close. Close to a reamer tolerance with a double margin drill. You can hold 5/10 all day with a double margin drill. So if your hole requests to be reamed, take a look at that ream tolerance, and if it's within 5/10, you might be able to get away with a double margin drill and not even use a reamer. Little tidbit for you, a little tip. Well, hey folks, thanks for joining me on this episode on drills. Whew, a lot of information. Hope you liked it. Hope you enjoyed it. Hope you're enjoying all these episodes. And next one, I gotta say spoiler. Normally I don't tell you what the next one's gonna be on. This one's gonna be on 3D surfacing. We're gonna talk about using ball, nose, and mills and getting the best surface we possibly can on our parts. This is great for the mold industry. It's good for aerospace. It's good for a lot of different things to understand how we can take a part that we hogged out and we did all this and we want to get a great surface on. How do we use a ball nose? How do we determine what scallop height we want? How do we determine what effective diameter is? Spoiler alert, see what I said? Effective diameter on the ball nose in. It's going to be everything ball nose, everything surfacing in the next episode. And a little spoiler alert, we got some friends coming by to visit us on the next episode. Not always wanted friends, but they'll be there in the next episode. Besides that, I hope you had fun. Hope you enjoyed this episode on drills. But before I go, 3 guarantees in life, folks: death, taxes, and spring passes. Have a great rest of your week, folks.